Hello everyone, and welcome to Understanding Physics, in which I will try to guide you through understanding physics. So, today on General Physics 1, we want to talk about conservation of energy, which is a continuation of the last chapter. So, we want to go ahead and start to actually think about the conservation of energy. So, first of all, what I want to discuss first are conservative force and non-conservative force. Non-conservative force. So what does this forces mean? Basically, basically a conservative force is a force that is applied to an object such that when it returns when returned to its initial condition, let me just put you down first. The work equals to 0. Basically, the sum of the work will be 0. So basically in calculus, the way that we'll actually write this down is the closed integral of the FDR, and this must be equal to 0. This is different compared to a non-conservative force, which is the closed integral of a vector dot dr. Vector is not 0. So what is the best way for you to think about this? So so the way that you will actually think about this is that let's just state that you are at like a plot, and then and then and then let's say you are pushing an object in a circle. Something like a let's just state that there is no friction here. So basically, if you push the object around a circle, every time your acceleration will go towards the center, which is basically meaning that the force is always pointing towards the center. And then if you try to sum up all of these points as well as its forces, the sum of it will be 0. This is the best way for me to explain this concept. Compare that to a non-conservative force. We will just do the same circular motion, but instead we will also add friction. Let's just take it as going in this direction. So that means that you need to push the object in this direction, as well as there's a friction going there. That means that you need to push it a little bit to the side like this. The sum of this, the friction, will later equal to 0, and therefore your force as well will also not be 0. So here is editing me trying to fix something that I stated a little bit wrong. So, what do you call something where its where its where its circular integral of f vector dot dr vector is 0? So basically the way that you actually describe this is that if you are doing a closed path, and so you know the f vector to be this one, and then the dr vector is going in this direction. Basically, if you do f dot dr and then you sum it, this would later equal to 0. And so this is one of the important things that you need to remember in doing these types of problems. And so there are also some other types of these situations. For example, if you are doing this in a square system, And so let's just take the force is always constant. So that means that the F dot dr here would be F dot the length, and then the one going in this direction would be the negative F dot L, while the others in here and here would later sum up to be zero, which will later be zero. And so this is one of the properties of a conservative force, unlike a non-conservative force, which will later be discussed using friction. So basically, if you do this with friction of this entire circular path, you would know that friction would go in this direction, while the dr goes in this direction. Basically, this will later result in a negative of the friction. Multiply that by 2 pi r, which is the radius of the star circle. So basically, this is where you would later require vector calculus. And so this is not zero anyways. And so this is one of the important things that you need to remember. How do you differentiate a conservative and a non-conservative force? Basically, a conservative force doesn't really care about the path that you are taking, while a conservative force really depends on the path that you are taking. So I hope this interlude helps you to understand what I was trying to state. So back to the video. And so this is one of the most interesting fact for you to always to remember about. It is that some things have a conservative force and some doesn't have a conservative force. And so why do we actually need to discuss about this? Well, we want to discuss about this because we want to talk about potential energy. Potential energy is basically the energy from a conservative force. So some examples of this include gravity or spring as well. So basically this doesn't depend on the direction that you are pushing it. This is one of the most important things for you to always remember is that the force, no sorry, the work that is done doesn't depend on its path. That is one of the things that you will later get from the calculus. So, to discuss the potential energy of gravity and the spring, we need to discuss what is the definition of potential energy, which I will state as the delta U from A to B will be equal to the negative from A to B of the F vector, the R vector. So basically this is the work from the first point to the second point. And why is it the negative? Well, this is the definition. It is like the same thing as we did last time, in which that if you actually try to pull an object, let's say like a spring, from a initial condition towards x, the work that you need is half kx squared. And so to balance this conservation of energy, you need to let the potential energy be the negative of this guy. It's negative half kx squared. And that's the change in the potential energy. Sorry, my bad. Well, basically the half kx squared comes... Okay. So why do we need the negative in this formula? Well, this will come from one of yesterday's example in which we discussed half kx squared to be the work needed to move an object from one place to another by a external force. That means the force from the spring itself will be negative half kx squared. And so the potential energy would be the negative in order to preserve the conservation of the conservation of energy, which should be zero. And so this is the best example for me to tell you about this. And so and so from and so from last video's formulas, we will later obtain that mg delta y will be for a potential energy, sorry, the gravitational potential energy, where this will be delta y. And then for a spring, it will be, let's take this is 0, this will be x, this will be half kx squared. So, after we have already discussed about potential energy, we can start to talk about one of the most important things that you will normally use, which is the conservation of mechanical energy. So basically, the conservation of mechanical energy is basically the conservation of all of the forces that are conservative. This is the main thing that you need to remember. So basically, the change of kinetic energy plus the change in the potential energy will later be zero, which means that the kinetic energy plus the potential energy should be a constant. And so this only works if there is no non-conservative force. Conservative force. So, what are the non-conservative forces? So basically, a non-conservative force will later relate with thermodynamics. But the way that I will discuss a non-conservative force is that you can't convert the energy into reusable work. It is harder for you to convert that back into energy that you can use. So one of the examples include thermal energy and 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 this is basically what we also call as internal energy, where you could actually where you could actually state that this is basically the kinetic plus the potential energy inside a molecule. And so you cannot really convert all of these kinetic and potential energy inside a molecule to be a energy of the system. So therefore, we would state this to be non-conservative because we cannot really use it again. This will later relate towards entropy, which we will later discuss at the end of the chapter. So we have talked about the conservation of mechanical energy. We will try to discuss the conservation of energy, which is basically almost the same thing. The change of the kinetic energy plus the change of the potential energy plus the change in internal energy will be the work from the external object. So let's just state that if you have a system, and then let's state I just put some work towards it. This entire system must to increase in its total energy, which includes kinetic, potential, as well as internal energy. So no matter what it is, the entire energy must to increase by the work, which is basically the statement of this formula. So we have already discussed about this, and so there's also another thing that I want to talk a little bit about, which is the potential energy curve. So what is this? So basically, the potential energy curve shows you a plot of the position. No, sorry. It tells you about the energy over position. So let's just state that as something like that. And so this is the potential energy U. And so why do we actually need this idea? So one thing that we will normally use this is to actually to observe what is the velocity on a object during a certain position. So let's just state if you have a certain energy, let's state here, and then you know your particle to be around here, therefore you would know that the object should be here. No matter no matter what you do to the system, as long as you have that amount of energy, your object should be in between these lines. But this is not true if you are starting to talk about quantum mechanics, in which that it could hop between these wells. So this is one of the interesting things that we will later discuss in quantum physics. But for now, let's just try to discuss this inside Newtonian physics. So we will use the same example as yesterday, but I want to emphasize more on the conservation of energy. So in here I have the same simulation as yesterday, but I also introduce some new lines, which is the boundary of the system. So basically in here, this is where the particle should be at, which is in between these wells. So basically if you have the energy to be in this black line here, your system should be in between these guys. And so if you actually try to run this, you would see that there is a oscillation. And not only that, basically in here the purple stands for the kinetic energy, while the blue stands for the potential energy. You could see that the sum is always on the black line. It couldn't be more, it couldn't be less. It is because I didn't introduce friction. If I introduce friction into the system, basically this will later dwindle down. But if you later include the energy of the thermal energy here, you would later see that the sum is always the same. And so this might seem to be weird, but in fact energy cannot be created nor be destroyed is the key component that you always need to remember. And so you could determine where the object is only through a potential energy curve. And not only that, you could also determine the force on the object, which I will later show you. So we want to talk about some other things that you could use in a potential energy curve, one of which is force. You could determine force to be the partial u over the partial x. So basically it is the derivative of u with respect to x. So how do you actually derive this? Well, the easiest way is to actually just to write this down as f dx to be equal to the negative u du. And then if you take the integral of these two guys, you would later obtain this to be the work, which is the negative of the change in potential energy. So basically this is the same thing with this. So this is one of the important things for you to know a potential energy curve, is that you could determine what is the force on the object thanks to this relation. So that's all for today, and I hope all of these information will be useful for your study in physics. So thank you very much, and I will see you on the next episode. See ya.